Okay, so now we're looking at even and odd functions. So the first thing that we need to know is that I don't want you to confuse this with an even polynomial. So an even polynomial is something like x squared or x to the fourth. That's not the same thing as an even function. An even function has this definition, that f of x is equal to f of negative x. So remember that f of negative x is a reflection across the y-axis. So if f of x looks the same as its reflection around the y-axis, that means that I'm symmetric around the y-axis. And of course, so this answer actually should be down here for what that means. All right. Oh, goodness. So I'm symmetric around the y-axis. So what that means is that my function y equals x squared is actually even. I know that that looks like this, symmetric around the y-axis, but I'm going to prove it this way. So when I prove it, I'm going to say if f of x is x squared, f of negative x would be negative x quantity squared, which is x squared. So they're the same. Therefore, it's even. But don't think that just because a function has an x squared in it, it's going to be even. So let's think of, for example, x plus 1 squared. Well, this is the x squared graph shifted 1 to the left. So that looks like this, which is not symmetric around the y-axis. So even though this is a quadratic, it's not an even function. And I can test that by using my definition. So negative x plus 1 quantity squared does not equal x plus 1 squared. So if I expanded g of x, I would get x squared plus 2x plus 1. If I expanded this one, I would get x squared minus 2x plus 1. Those are not the same. So this means that just because it's an even power doesn't mean it's an even function. I have to use this definition to be even. All right. An odd function has this definition. So now an odd function, let's go with purple for odd. F of negative x equals negative f of x. So graphically, if I think about that, if I take a function and reflect it over the x-axis, it's the same, this is my reflection over the x-axis. It's the same as if I reflected it over the y-axis. Well, an example of this is x cubed. So let's look at x cubed. So here's my x cubed graph. So parent function looks like this. If I think about negative x cubed, that means I'm going to take this and reflect it over the y-axis. Sorry, misspoke. I'm reflecting that over the x-axis. So negative x cubed, I'm going to take this and flip it over. So this part's going to come up top. This part's going to go down the bottom. And if I think about negative x quantity cubed, well, that's going to take this function and reflect it over the y-axis. So this bit will come over here. This bit will go over there. And I can see that these two functions equal each other. Those are the same picture. So graphically, what it means is that this graph, So my two reflections end up making the same picture. Really what it means is that I'm symmetric about the origin. So if this reflection maps this reflection, basically what it's saying is that through the origin, I'm symmetric. So think about mapping across this point. So any points are going to mirror to the other side of the origin. So these are symmetric. So the original is symmetric about the origin. That's the point 0, 0. Or I can think that reflection over x is the same as the reflection over y. But algebraically, I'm going to take f of x equals x cubed. F of negative x is negative x cubed. Of course, that is going to be negative x times negative x times negative x, which is going to give me negative x cubed. Negative f of x means I take the negative and multiply it by my f of x, which of course is negative x cubed. So now f of negative x equals negative f of x. Therefore, my function is odd. Again, just because I have an odd power doesn't mean I'll become an odd function. I always have to test it with my equation. So let me go back to my highlighter and highlight this again, that this is our statement of proof. We can use this to help us look at things, but I need to do my algebra to show a function is odd or a function is even.